So recursion and iteration are both ways that we can repeat something over and over again. Iteration allows us to use a loop to repeat the same code, and recursion uses method calls of the same method repeatedly to again do the same task over and over again. With recursion, we think about kind of making the problem smaller. With loops, we usually, define the beginning and the ending of the iteration, the repetition when we define the loop. But they're both ways to repeatedly execute some statements. Any problem that you can write with recursion, you could also write with iteration and vice versa. If you have a problem that uses a loop, you could rewrite it with recursion. So you always have this choice of whether to use recursion or to use iteration looping. So just because you can use iteration to solve a problem doesn't mean you should. So for example, we looked at the problem that sums up the integers from 1 to n. That looked like this, the sum to 1. We looked at it using return statements and with local variables. But that problem could be very easily accomplished with a loop, right? We could just declare the result as 0, then we could just loop through from 1 to n and add each one of those numbers onto I and return that value. So this problem is very easily implemented with iteration. Now, that's not true for some problems. Some problems, the recursive solution really is a much better solution. It's much easier to understand, it's much easier to write, it's less error prone, things like that. But there are times that for a lot of cases, you can use recursion, but iteration is just as clear, or in this case, I would say even clearer, and oftentimes more efficient as well. So which one you want to use is an important design decision. So some things you want to think about is how clear is the solution? So you want to make sure that someone else coming in and reading your code is going to be able to understand what's going on. So a lot of times the recursive solution can often be easier to understand because sometimes it does sort of mimic the way we think about things in terms of breaking a problem down into smaller pieces. How easy is the solution to program and test? So is the iterative solution incredibly difficult to write, and is it going to be very buggy? Is it going to be very prone to errors? Is it going to be easy to test? Those are things to think about. Is your solution reusing information in the best way? So we're going to look at a problem in a moment where you'll see that the recursive solution is actually recalculating things over and over again. So that's not good. So in general, you want to, reduce any repetition that you have in terms of repeating the exact same code over and over again. How efficient is the solution? So this is usually the biggest thing we want to think about is efficiency. So usually this is the thing we should probably think about first. And then if we have a recursive and an iterative solution that are sort of equally efficient, we might think about these other things. Because if the recursive solution is less efficient, even if it's clear, and maybe clearer to understand, easier to write, we might not want to use it because of that efficiency. So most likely if you're dealing with a program that uses any sort of real world data set or real world communication with users, you're probably talking about a program that needs to be efficient. And so efficiency should probably be your first consideration. But then assuming, let's say, that the recursive and iterative solutions are equally as efficient, you might think about these other things. The other thing you do need to think about is what language are you using? So in Java, Java doesn't do what's called optimizing for recursion. That means that Java always keeps methods on the runtime stack until the method completes. Even if, let's say, the recursive call is the very last method call in your program, nothing has to happen after it. So in theory, Java could kind of clear that method off the runtime stack because it doesn't have anything else to do. Java does not do that. So that kind of recursive method is called tail recursive, and it's good because it allows languages that do optimize for that to kind of improve their efficiency related to recursion. But Java doesn't do that. So you have to keep that in mind. If you are using a language that does optimize for that, your recursive solution might be able to be made more efficient. With Java, you are limited by the fact that you can only have so many method activation records on the runtime stack before your program will crash. So these are all kind of things to think about. Let's just quickly look at some iterative solutions to some of our previous recursion examples. So we started off with just our basic blast off countdown example. So this one would be pretty easy to write iteratively, right? We could just have a void blast off countdown iterative, take in the number, and we could just use a simple loop, right? We could say for int I equals n, I is greater than or equal to, what do we leave off at 1, I minus minus. we just print out the number. And then when we're all done, we print out blast off. Okay, so that is a pretty simple solution to write iteratively. Okay, similarly with factorial. So here is our recursive factorial. We could also write that so that blast off was a void method. Here we have our a recursive valued method, factorial. We could also write a factorial iterative, again taking in our number, and we could say, well, the solution will start with 1, and then we can just say for int I equals 0, or sorry, I equals n rather, I is greater than or equal to 1, I minus minus, and we can just say that the solution equals the solution times n, or times I rather. Okay, so this will allow us to multiply, n by an n minus 1, then by n minus 2, and so on and so forth, down to 1, where it'll just multiply by 1, and then of course we return that solution. Okay, so easy to write the iterative version of these. I think that both of these methods that I just showed you are pretty easy to understand, both recursively but also iteratively. The iterative solution is pretty easy to write and pretty easy to understand. You might think that probably that's the case too for, printing all the characters out in a word. You could just use a simple loop, go through and get the character at each index and print it out. For doubling the elements in an array, again, you can just use a loop, go through, double the elements at each position for an array or for a list. For our valued methods, summing up the numbers, that's what we just looked at on the slide. Reading user input, you could just use a simple while loop and keep looping while the user gives you bad data and exit the loop when the user gives you good data. Counting characters, again, you can just use a simple loop and look at the character at each index. So I would say most of the examples, probably all of the examples that we've looked at so far, recursion isn't really needed. The iterative solution is pretty clear, it's easy to write, it's efficient. There really wouldn't be a real reason to use recursion. And this is one of the things that makes recursion very difficult to learn, because usually all of the examples that we look at with recursion, they could be easily done with iteration. So it kind of leaves you thinking, what is the point of this? Why am I learning recursion if all of these problems can be just as easily solved with iteration? So what's challenging about that is that the cases in the real world that could actually use a recursive solution, they usually involve much more complex data structures that you're not necessarily expected to know when you're learning about recursion. So this is things like trees and graphs. A lot of those data structures have a natural solution approach using recursion because of how the data structure is used. So that's what makes this kind of tricky, is that the examples that we use aren't necessarily really what problems you would solve with recursion. But it's important to understand that there are solutions in the real world that are much easier to write and understand when written recursively. So it is important to know about recursion to be able to write recursive methods, to be able to trace recursive methods, even if you might not use them until you get a little further along into using more complex data structures. So we are going to look at one example of a mathematical problem that I would argue that the recursive solution is much more easy to understand when written recursively. So this is another kind of classic recursive example that you'll see, and it's the example of the Fibonacci numbers. So the Fibonacci numbers is a series of numbers. These numbers show up in lots of places in math and in science. They appear in different patterns in nature, so they're kind of all over the place. If you've never heard about them before, I strongly encourage you to kind of, give it a Google. Even the Wikipedia page has some great examples and information on it. So, kind of look it up. They're a pretty cool sequence of numbers. But essentially the sequence, what it is they start with 0 and 1, and then they're calculated just by adding the previous two numbers. So you have 0 and 1. Then the next one is, this should be 0, 1, and 1. Sorry. Then we add 1 and 2 to get 3. We add 2 and 3 together to get 5. We add 3 and 5 together to get 8. 5 and 8 together to get 13. 8 and 13 together to get 21, and so on and so on and so forth. So you calculate each next Fibonacci number by adding up the preceding previous two numbers. Okay, so you can see how this makes an obvious recursive definition, right? And again, I'm missing that 1 in here. There should be another 1 in there. I'll add that to the slide. So the first Fibonacci number is 0. The next one is 1. And then for every other number, you just add the previous 2 together. So the next one's going to be 1. And then you add those 2 together to get 2. Again, add those 2 together to get 3, to get 5, and so on and so forth. So we have a recursive definition that really makes a lot of sense for this sequence of numbers, because we're defining what a Fibonacci number is, and we're defining it in terms of a Fibonacci number. So that is a recursive definition. We have our base case. We have our first 2 Fibonacci numbers of 0 and 1. So that's when we know when the recursion should stop. So this is pretty easy to understand, right? Anytime you need to calculate a Fibonacci number, you just add together the 2 previous numbers, and you just keep doing that back till you get down to your base case. And that's how you can figure it out. Okay. Now, I should make a side note that sometimes people say the Fibonacci numbers start with 1 and 1, and sometimes people say they start with 0 and 1. That really doesn't matter for our purposes. The idea we're just using these numbers is to look at how they look when you're writing them recursively. Okay, so don't worry about that distinction. You will see some places start with a 1 and a 1, and other places start with a 0 and a 1. So the recursive solution to this is very easy to write. We just have our base case. If n is less than 2, we just return the number. So basically, if n is 0 or 1, we just return that number. We return a 0 or we return a 1. And I'm using these base cases we've defined here. Otherwise, we just return the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. So here we just combine the 2 recursive calls of n minus 1 and n minus 2, and we add them up together. So here we have a valued method. We are returning the value of the recursive call, so we're keeping track of it. We could also use a local variable. That would work too. So this is a very easy solution to write. But when you start to think of, and to understand, but when you start to think about what actually happens when this executes, you'll see that you are repeating yourself a lot. So let's say we want to calculate the Fibonacci number of 5. Well, to do that, we have to calculate 4 and 3. How do we calculate 4? We calculate 3 and 2. How do we calculate 3? We calculate 2 and 1. How do we calculate 2? We calculate 1 and 0. Those are our base cases. Again, for 3 here, we get a call to 1. For 2, we get 1 and 0. For 3, we calculate 2 and 1. Again, 2, 1, and 0. So this is kind of all of the recursive calls that will be made. But what you can see here is that we're calculating a Fibonacci number of 2 3 different times. We're repeating that same calculation. We're repeating the calculation of, the Fibonacci number of 3 2 different times. And this is for a pretty small number, right? We're only asking for the 5th Fibonacci number. So as you get into bigger numbers, you're going to be repeating way more calculations. So that's not good. You can also see here that we have this sort of growing explosion of calls, right? So for 5, we need to do 2, and for 4, 2, and for 3, 2s, right? So we're kind of growing the number of recursive calls, and that makes sense because every time we enter a method, we recursively call that method 2 more times, okay? So this is not an efficient solution, all right? This is actually very inefficient. The iterative version is efficient, but it's not super intuitive to understand. So this is an iterative solution. You can kind of trace through this and convince yourself that this will work, but it's just an iterative way of finding this Fibonacci number. So it's the same result as the recursive version, but you look at this and it doesn't immediately jump out why it works, right? Whereas the recursive solution is very clear how it's working. So this is a case where the recursive solution is much easier to understand, but the iterative solution is much more efficient. Okay, so the recursive solution is actually on the order of 2 to the n, so it is exponential. So that is terrible. We never want to write algorithms that are that efficiency if we can help it, right? There are some problems that can only be solved that way, but Fibonacci isn't one of them. This iterative solution is only going to loop through this loop on order of n, right? Basically n times. So the iterative solution is O of n. It's linear. That's ridiculously more efficient than this. Okay, so in this case, even though the recursive solution is easier to understand and it's kind of more logically in line with the mathematical definition, in reality, you wouldn't use that for programming because it's so inefficient. If we take a look at the code, so here I've just put the 2 methods that you just saw on the slides. I've just put them into our program here. So I have the recursive and the iterative. And I also added some counters. So I added a recursive method counter so you could just see how many times we get into that method. And I added a loop counter so we can see how many times we pass through the loop. I also added in some timing. So we're just going to see how long it takes to find the solution iteratively and to find the solution recursively. So let's start out just running this with, 5, the Fibonacci number 5. So we get the solution of 5. That's for the fifth Fibonacci number for both cases. If we find the Fibonacci number for 10, we get 55. So it's again the same number. That's good. The time is pretty comparable, but look at how many times we're looping through things. So to find the 10th Fibonacci number with the iterative version, we took 10 passes through the loop. With the recursive one, we made 177 recursive calls. So here's where you can really see that difference between the linear and the exponential. So keep these numbers in mind, 10 passes through the loop and 177 recursive calls. Let's double this to find the Fibonacci number 20. We now get 20 passes through the loop and we get over 21,000 recursive calls. So again, your recursive calls are just exploding with this Fibonacci recursive solution. So this is an example again where the recursive solution is much clearer, much easier to understand, but in reality you wouldn't want to use it unless you knew that you were always going to be finding pretty small Fibonacci numbers. Once you get up to, I think it's 40, you get to a point where we're not even going to wait for this to finish because maybe that actually isn't too bad. I think maybe 50 is where it started. Right around 50 or 60 is where you're not even going to wait anymore for it to get through because it takes so long. Okay, so that's an example of that. Again, the recursive solution, I think, is much easier to understand, but it is much less efficient. Okay, but this isn't always the case. So there are some problems where the recursive solution will be easier to understand, like it is for Fibonacci, but will also be equally or sometimes more efficient. Could be more efficient than the iterative version. So that is possible. And again, one of the reasons that we don't necessarily focus on those examples is because those problems where that happens tend to be problems that use really complex data structures. So we can't really include them into this topic of recursion, but it's just really important to be aware that there are problems out there where recursion is the best way to solve the problem. Okay, so I think it's just unfortunate that a lot of times when people first learn recursion, they kind of think like, this is, why am I doing this? All these problems I can just write with iteration. And some of the ones that look much easier with recursion aren't efficient, like Fibonacci. So what's the point? But again, there are real world applications where recursive solution is easier to understand and it isn't less efficient. So it's a good choice. Okay. One last thing to think about is that, again, in Java, you do always have to consider that runtime stack and the possibility of a stack overflow error. So I think I forget where we get the stack error, but if you ask for the Fibonacci number, if you keep increasing this number and then wait long enough, you will eventually get a stack overflow error because basically you are putting too many recursive method calls on the stack runs out of room, throws an exception, program crashes. Okay, so you have to keep that in mind with Java. You can do more iterations in a loop than you can do recursive method calls. You can do that many iterations in a loop, some really big number, and your program won't crash. If you try to do that same number of recursive method calls, you might get a stack overflow exception. So just something you have to keep in mind with Java. But again, not all languages are like that. Some languages optimize for recursion, so that's not something you have to think about. One last note about iteration and recursion. In general, we do not mix them. So usually if you are mixing iteration and recursion, it is a mistake. So a common error that I see is sort of a recursive method. And instead of putting an if, sometimes people will put a while here. That is very bad. So instead of some if condition telling you when to stop the recursion, sometimes people accidentally put a while loop and then have a recursive call in there, and this leads to bad things. It just leads to kind of explosions of code and of memory space and things like that, and it will definitely crash your program. I shouldn't say definitely, but it will most likely crash your program. And this is nearly always a mistake. So in general, just be careful about things like this. You almost never want to mix recursion and iteration. There are some cases where you want to repeat a recursive call more than once. Like for example, it'd be kind of silly, but you could do a for loop in Fibonacci and say for I equals 0, I less than 2, invoke Fibonacci with n minus I. Okay, so you could do that. That would be an example of putting a recursive call inside a loop that would be okay, because that loop isn't being conditioned on some outside, isn't being controlled by some outside condition. It's a set number of times that you need the recursion to happen, and that's okay. But this whole idea of waiting on some condition inside a loop and that condition's being changed by the recursive method, that is wrong. You don't want to do that. Okay, so just be really careful about that. This is almost always just a typing mistake where people mean to put in a conditional and they put in a loop instead, like a while, and it's usually a mistake. So I always say that this is like feeding gremlins after midnight. Just don't do it. It can lead to bad things. And if that reference ages me, hopefully some of you out there find the humor in it. If not, you're not missing anything. Don't worry about it. But anyhow, just be careful about that iteration and recursion. In general, you don't want to mix them. If you are mixing them, you want to be careful that you're doing it in a way that is necessary and thoughtful.